Hey everyone, welcome to another episode of Robo Papers. Today we're super glad to have Zhi Su with us today. He's one of the co-authors of this paper called HITTER, a humanoid table tennis robot via hierarchical planning and learning. Yeah, super glad for you to make the time, Zhi Su. Maybe as a start, if you can share a little bit about yourself.
Yes. Okay. So, I'm now a senior year undergrad in Tsinghua University, and I did this project when I visited UC Berkeley. Yes, with the cultural arenas and also Shankar ancestry.
Undergrad, what substantial contribution have I made to this world? Probably zero. I think it would be nice if it's not negative. And then you just go and do your thing. 3 months later, you got this paper done. I think it's really, really impressive.
Today's talk, I will first talk about the background, like the motivations, why we did this project, and I can show some demos and also dive deep into the method parts, like the system overview and the two main parts of the system. And also I will talk about some limitations of our work. So the first part, the background. So we observed that the most recent humanoid work mainly focuses on interaction with static ground, like doing this balancing or cartwheel things. And so we wonder, can the humanoid robots do some rapid interaction with the dynamic environments, like move very faster objects, like the table tennis. Okay, so let me first show you some demo video of the paper. I think some people might have seen this video. So our system supports the humanoid versus humanoid of the system.
So
and also a humanoid versus human.
So robot playing table tennis, right? Playing ping pong.
And the forehand and backhand switch deal with a very deep ball.
And just so we understand what's happening here is this being tele-op or?
No, it's fully autonomous. The robot is controlled by an RL policy.
How is it perceiving? Can you tell us about how it's perceiving the ball? Like it's doing this really with onboard sensing?
Yeah, I will dive deep later, but
in more detail.
For a short response, the mocap system received the position of the ball. So you can see here the ball is covered by some reflective tape.
Makes sense.
So I think the motion is quite human-like. And also we do some extreme tests, like let the robot and the human play for over 100 shots.
It was 100 in a row without messing up on the robot's part. That's impressive.
Side step.
And also the side step movement is very agile. Also, we let the robot play faster against the robot.
Returning smash.
Yeah, so it looks like you're still better than the robot, but not by too much. Is that right?
Sorry?
Looks like you're still a bit better than the robot, but maybe not by too much. Is it?
Yeah.
All right.
So this is the success rate experiment. I think the success rate is very high, but there are also some failure cases. Like the robot didn't hit the ball or hit it but cannot return it.
Yeah. But I think it's important that these are all fairly unconstrained, right? It's really we've seen people have done stuff with playing tennis before, but it's always been a fixed base arm and this feels like a very natural setup where you could really play with this robot like a person.
Yeah,
kind
true.
Of. Is that, yeah.
I think.
And that makes things a lot harder. That's impressive. Yeah, okay, go ahead.
So let's first look the system overview. So for the robot parts, we directly attach the racket to the robot via using 3D printed connector. And for the ball, we attach some reflective tapes over the ball to let the mocap system detect it to get the position of the ball. And also, I think we didn't show it here, but the pelvis of the robot is also covered by some reflective balls to guess the position and also the orientation of the robot. And so after we get the position of the ball, the model-based planner can predict the trajectories and also plan the time, the position, and also the velocity for the racket to strike the ball. Yeah, and this information is then inputted to the observations and fed into the policy to control the robot. For the learning-based whole body controller, the policy is trained with the reference motion to make it more human-like.
Is the policy run locally on the robot? It's not,
yes,
right? It's run.
The policy is run on the robot, but the model-based planner is run on an external computer.
Yeah, because that's the one that's receiving the latest information of the ball, right?
Sorry?
So the information of where the ball is going, that one is in the external, not in the robot, right? Because I suppose it's running somewhere.
So the mocap system first get the position of the ball, and the position of the ball is go into the external computer, and the computer computes the time, the velocity, and the position target for the racket, and this information is then go to the robot. Then
so basically, so you have the whole body controller so you've trained your whole body controller through reinforcement learning so that it let me repeat so that you can tell it, like, I'm going to be at this position and I'm going to move this fast so I can hit the ball so I can return it. And then you've trained it on a bunch of those, and then the model-based planner comes up with these trajectories that tell you just that why do you need the model-based trajectories?
So I think we try to train the whole system end to end from just in a simulator. So you have the table, you have the robot, and you have the ball, and you want the robot to return the ball. But I actually found that because the reward is very sparse, like there is only a reward when your ball landed on the other side of the table, and it's actually very hard for the policy to learn some, So it's even very difficult for the robot to hit the ball, so not say returning it.
Yeah.
So we finally ended up with this hierarchical setup to first let a model-based planner plan the time, position, and velocity to hit the ball, and let the policy learn to track these commands. So this is easier than the end-to-end way.
Yeah, makes sense.
Can you talk a little bit about the whole body control? Like you mentioned here, train with reference motion.
Yes. So
what are these reference motion?
So the reference motions. So we have two reference motion. The first one is the forehand swing, and the other one is the backhand swing. So I think I have some more slides later about this.
Okay.
How we train the policy with the reference motion. So first, I want to dive into the model-based planner part. So it's the task for the model-based planner is to predict the time, position, and velocity target for the racket. And we assume that when hitting the ball, the rackets are vertical to its velocity. So we don't need to predict the orientation command here. So its task is to predict these three information from the position of the ball. The position of the ball is observed by the mocap system. Because the mocap system can only get the position of the ball and it cannot get the velocity of the ball. So we first need to do some things to get the velocity, like using the curve fitting. And then since we get the position and the velocity for this single time step, we can build a dynamics model and do explicit integration, a step-by-step time integration to get the time and position target for the racket here. And then by using the desired landing position, we can do some computation to get the velocity target.
How do you decide what is the desired landing position?
So basically, the desired landing position is just the center of the other side of the table. But since we use a very simple dynamics model, the ball cannot land it very accurately at the desired landing position. So our goal is just let the ball land on the other side of the table, make the desired landing position the center of the other side. So by curve fitting, we first collect 31 recent points. It's about 0.1 second because the mocap system is running at 360 Hz. And then for each single dimension, we fit second order polynomial of the trajectory, like the px, py, and pt of time t. And then by evaluates the function and also its first order deviation at this time step, we can get the position and also the velocity of the ball at this single time step. And then to predict the time and the position when the robot's trajectory enter the virtual hit plane, we can do step-by-step time integration. So first we build a hybrid dynamics model. When the ball flies on the air, it has two forces. The first one is the gravity, and the second one is the air drag forces. So we here ignore some forces related to the angular velocity. And also when the ball bounces on the table, we build a model like this model. And the CH here is the horizontal restitution, and the CV is the vertical restitution. So the CH here basically is the friction of the ball and the table.
Yeah, so I suppose at least for this paper, you don't consider the spin of the ball,
yes,
right?
For real. So I think there are several parts. Okay. So first, if you want to estimate the spinning, the angular velocity of the ball is also very difficult for the mocap system to do this, since the mocap system can only get the position of the ball.
Yeah, got it. Okay.
So we ignore the angular velocity here. And also, so here there are three parameters, the K and also CHCV. So we fit these parameters by collecting 15 trajectories of the ball. So for each trajectory, we mean that the ball flies from the one side of the table and bounces once on the table and then exceeds the table. So this is one trajectory. We collect 15 of them and fit these three parameters to get a more accurate model. And then we have this model, so we can just by doing some time step-by-step integration to get the position and also the velocity at each time step, at each future time step. And then find the position, the point that the trajectory intersects with the virtual hit plane. So we get the time and also the position of the racket, the position target of the racket. And the next part is how we get the velocity target for the racket. So we also build a very simple model. So for the simplicity of the computation, we just after the ball out goes here, so we just consider the gravity force and ignore other forces like the air friction or anything else. So by predefining delta t, the ball flies on the air. So we can directly compute the outgoing velocity of the ball here, VO. And since we can predict the velocity, the incoming velocity VI of the ball, and we can then build a very simple collision model of the ball and the racket. Here. So the CR is the restitution of the collision, and we directly just ignore the friction. So then we can compute the velocity target. I think that's all for the model-based planner part, from the position of the ball to the time, position, and velocity target command for the racket. And this is some experiment results like showing the very low error of the prediction system. The critical error here is the 7.5 centimeter, which is the radius of the racket.
Sorry, so what is this time until strike? Could you explain a little bit what is?
Yeah, so the time, so this 0 point is a time at the hit time. We show the arrow decrease when the hit time approach. So the 0.6 is here, 0.5, 0.4, 0.3, and 0 until hit.
So basically, if the robot can move fast enough that it can move, it looks like maybe 5 centimeters in 0.3 seconds. Can it move that fast? Then it should basically always be able to hit. Is that the idea?
Yeah.
Yeah.
I think the idea is here, since our prediction error is very low, the robot can have enough time to go to the desired position and then hit. Okay.
And so,
So
this all
next
feeds
is
into
the
your whole body control. Yeah, cool.
yeah, and then it's the whole body controller. So we fit the predicted time, velocity, and also the racket target to the policy. And the other parts is like the base position command for the robot is computed heuristically using the racket command and also the actual position of the base. And this relative information and also the orientation of the base is then inputted to the whole body controller, the policy parts. And the policy is also trained using the human reference to make it the motion more human-like. So I think there are basically two parts we should pay attention to. The first is how I train the policy with these commands, and the other part is how I train it with the reference. So the first part is about command design. I think I can first show you an episode of the policy running in the simulator. So you can find here in the simulator there is no ball here, because in the model-based planner we separate the ball with the racket target position. So in the simulator we can only sample lots of commands of the racket and let the robot check the racket commands here. So you may notice that there are several consecutive commands in each episode. So using these consecutive commands, the robot can learn to return consecutive balls. And also we separate the commands for the lower body and the upper body. So you may find here there is a command point, the green dot here for the lower body, the base position command, and also the racket command for the upper body. But our policy is still one policy control the whole body. It's not separate policies. So the first command is the desired base position command for the lower body and the racket target time, the position and velocity for upper body. So you may notice here we directly use the position command. Like other paper may use the velocity command. So actually at first I tried to use the velocity command and let the model-based planner also plan the velocity command for the robots. Found that there is a latency between you input the velocity command to the observation to the policy, and the robot actually moves at that certain velocity. So this latency is very harmful to the highly dynamic tasks. So we finally ended up with this position-based command. Yeah, and the
sorry, just but the position, does it have a time component to it?
Time?
Does the command say, your lower body needs to be at this point, which is the position, but within a certain time?
Yeah, so when training, we only add the reward terms before the hit time, which means we want the robot to be at this desired position before the hit. And after the hit, there is no need to constrain the position command. Yeah, so
after the hit, you just have normal kind of safety rewards, keep the robot standing, so then it just finishes its swing through, gets back to... Okay, makes sense.
Yes.
I guess I'm also curious about the racket. So here you have the target time, position, but also the velocity. So velocity, I suppose, in order to achieve the velocity, once it passes the target position, it will have a follow through, right? In order to continue the velocity, like it happens after that. Like once it hit this position at the desired velocity, what does the model learn to do? Like, does it go to a more natural position? Or, you see what I'm saying? Once you hit a velocity, okay, you got the velocity, but what is the signal to tell the arm what to do next?
So the racket target position only applies to that single time step, only as the target time step. But after and also before the hit time, we have some checking reward to let the robot check the reference motion. So I will discuss it later to check the reference motion to make it more human-like.
Okay. I see.
Yes.
Cool.
Do you have anything to get into the middle of its workspace or something? So or I guess maybe workspace is wrong. But when you're playing, you would want to keep you want to keep ready. You don't just want your hand to drift up or down, right? You want to be at a reasonable position so you can be ready for the next strike.
So I think it's...
Or did that just kind of come out from the human reference data? Yeah.
Yeah, I think that the robot does not
It just okay.
present that behavior in real world. Yes.
I could also imagine getting that from the human reference data at some point. That makes sense. Okay, cool.
Yeah. Sure. So for the human reference here, we only have two reference. The first one is the forehand swinging and also the backhand swing. So to make the robot check this human reference to make it more human-like, its motion more human-like, we directly add the other term to the reward, the imitation term, which is checking the reference, the motion reference. So the goal, the RG, the goal term here is the previous discussed the base position command and also the racket position, the racket commands, and also other regularization term like the action rate or something else. So we only imitate the upper body reference motion and let the lower body directly trained by RL to like reach the desired landing position, the desired position for the base. And since there are two reference motion, we should determine which one to check when training. So it's determined based on the racket position command. So if your racket position command is here on the right of the robot, we let the robot check the forehand reference. And if the position is sampled like here on the left of on the left of the robot, we let the reward check the backhand motion. So this is the very simple composition of the imitation reward and the goal reward is from deep mimic. So I actually consider like if it might doesn't work, so we might need some fancy method like AMP or what. But yeah, I tried this and it works quite well. So yeah, I think there's no need to use more fancy method like AMP or something else.
And sorry, Zhi Su, for the when you say this, forehand and the backhand, is it literally just one motion?
Yeah, it's just one motion.
Just literally one.
No, just one. Just one.
One demo, and okay, I see.
Yeah, one forehand and one backhand, and each is like 2 seconds.
Do you think it needed this? Do you think it would learn better without it, or do you think it? Did you try both?
Try like. So
do you think you could just get by with the reward, the RL reward that you were talking about in the previous slide, or do you think do you need the human reference?
Yeah, I think we actually very need the human reference. So I tried to do some ablation study like without the reference motion. So I found that the result is motion is very weird for the robot. So it will.
Do this to the,
so you do need it. Is it very weird and like weird bad, or just weird like inhuman? I guess.
Like it's not human-like, I will say.
Okay.
What?
Do you think it would be? But would it be better or worse at playing tennis? I guess is that.
Yeah, it could be robotic-like, but then maybe it's superhuman, in capability.
And also the training will be slower without the human reference, because the human reference can serve like a guidance for the racket position, like for reach the racket target.
Yeah. You could anneal the reference down to 0, like the weight down to 0 or something, and then say, I don't know. Yeah, but yeah, you're right. Yeah, it would definitely be slower.
Yeah, maybe.
Yeah.
No, I'm curious.
Sorry, it's okay. Do you think it would? Do you think it would still be able to do it?
It's able to do.
Or is like the search the RL problem so hard you couldn't do it without the reference? I guess.
So I think it's just take longer time.
Okay, so you think it would be able to do it, but it would take a really long time and it would look pretty weird. I think that makes sense.
Yes.
That's cool.
Sure.
Okay. Yeah.
I'm also curious, have you guys considered like having just more like, forehand? There are many style of forehand. I guess in this particular paper, you guys just use literally just one sample. But if you were to do like to incorporate something that actually incorporate different, like more than one, just one, literally one. Even the same player, like you do it 10 times, it's just slightly different every time you do it.
Yeah.
Would it have changed the way you set this up a lot?
If there is. So for this specific setup, like we just want the robot to hit a position, generate human-like motion. I don't think there is a need to introduce more reference motion. But if you want the robot to generate other type of the returning, like you want it to spin, like chop or what, So there is a need to use more reference motions. And the training pipeline will differ a lot, but I don't think I have an idea now to how to incorporate so many reference motion here.
Well, I mean, I guess in a way you already have two distinct reference motion, and you have this branch that says that, okay, at inference, okay, do I infer the forehand or the backhand, right? And in a way there are already two style already that you have. It's just that with each style there's literally only one reference motion, one episode of reference motion. Okay, cool.
So I think basically the method part is done, and I think I can discuss about some limitations. I think since our work is the first one, try to explore the movable humanoid table tennis. I think there are a lot of limitations left for the future work. So we use a predefined virtual hit plan just at the end of the table. So this constrained a lot of the returning position. So this make the robot very difficult or impossible to return very short ball. And I think, and another reason for the short ball is the hardware, because the robot we use is Unity G1 is very small. So if we want the robot to return very short ball, we might need taller robots. Yeah. And also the simplified model, we directly ignore the spinning here. So yeah, it's very difficult for the robot to return highly spinning balls. And also we use the external mocap system, which makes the system can only stay in the lab environment, and we cannot bring the robot outside to play like outdoor robots like anywhere else.
Yeah, suppose for the external mocap, it's purely used to track the ball trajectory, right? So in theory, if you one day have a new version, I don't know, G2 or G3, where the neck can actuate and, the camera is really good, and basically you can infer just based on vision the trajectory of the ball very accurately at high enough frequency, you will then just replace that part of the stack with that, right? And it will still work.
Yes. I think we might do not need the prediction part, because if you consider how we human play the table tennis, no one predicts the trajectory. We directly use the position of the ball and maybe some previous time step of the image, RGB image, and directly predicts how we hit the ball.
So now you've got this robot though that can do it, right? Like it can perform the task. Could you just collect a bunch of data from that and train a vision model, train one that can do it just like a human can?
Mm-hmm. I think for the future it's possible. So theoretically it's possible.
Yeah.
I would think.
I mean,
yeah, cool.
Yeah, the G1's, at least the default camera that comes on the head, actually is pretty narrow view.
Yeah.
So but
makes sense.
They also don't have an actuated neck. So
yes. I think the net actuator is very important.
Okay, so you need
for the check of the ball.
Back to needing a better robot. Okay.
Yeah. Well, you need active vision. So you need the neck so that your I think you need.
Yeah, I think you need a human active neck.
Active vision, to move the camera,
Sure.
And probably you need stereo to help you tell a bit of depth. We used to. I think if you ask a professional ping pong player to just close one eye, it will be extremely hard. It's very, very hard to tell depth.
True.
Yeah. How about the hardware? I mean, as you're doing this, I play a lot with G1s lately, and some of the actuators do overheat. It seems that the rally, I was quite surprised. It go on for quite a long time. How long when you were doing the experiments, do you think the hardware was posing this kind of constraint for you?
No, I don't think so. Because we can consecutively do the experiment for 20. And then the robot will just collapse. I don't know why, but after it collapses, I felt the heat of each motors, but I don't think it's overheat. I just don't know why.
You just want to, okay, give me a break.
Interesting.
Give me a break. Interesting. Yeah, I imagine like for ping pong, it's like literally the impact is almost like is definitely within the spec, like way below the spec. But I imagine if it's tennis, like literally hitting the ball,
Yeah.
it's gonna impact the actuators a lot more. Yeah. So I think ping pong is
Yeah, because
actually like for something like a G1, I think makes sense. Interesting.
because
Um,
the weight the weight of the ball is very light for the table tennis. So for tennis, the arm actuator will like use much more
I think the
forces.
shoulder, yeah, the shoulder actuators will overheat very quickly. Yeah, yeah. So I guess now that you've done this, what would be? I mean, you kind of talk about it a little bit, but what would be some like further work that you love to you yourself do, or like see other people also try?
For like I'm not sure. So for this series, the like for the ball sports for humanoid, I think there are still a lot of different things to do, like badminton, the tennis, because they are similar to the table tennis, but they may focus on different points. Like the badminton or tennis requires the large range of movements, and for our table tennis, the robot just take one side step at each round. And for badminton, for tennis, it requires the robot to move a lot. Yeah, there are some challenges.
I'm curious, like how quickly did you get from like did things like just start to kind of work like as you do this? Because I mean, so many teams have tried to attempt this table tennis with a robot thing, I think for years. And but I mean, as you said, you guys are the first time to try with the humanoid and actually make it rally for the rally was very impressive. But I'm curious, like which part of it was something that like was a big hiccup that like that you didn't even know whether you can fully solve to have something like this, or was it kind of smooth sailing?
I think because I just did this work for like 3 months. I think it's actually very smooth. Like for each
If it hadn't been
single
smooth, it wouldn't have
challenge,
gotten done. It was at the yeah.
for each small challenge, I can solve it for days, and there's no need to. There's no cases like I stuck there for several weeks or even months. So I will say it's very lucky.
Yeah, that's awesome. The research gods were with you, right? Where you were doing your just thing at Berkeley. That's awesome. Yeah. I think for me, it's like demos like this is eye-opening to me because it proves what the hardware can do. Until it can be done, and then you don't quite know what is the limitation of this hardware. So clearly G1 can, for what it's worth, like it can actually do a lot if you set it up the right way. Certainly the mocap is a big limitation, I would say. But still, I mean, you still end up getting the humanoid to actually have a decent rally with a human player, which I thought was super impressive.
Yeah, thank you.
Yeah, I feel like what struck me about it is that unlike most demos that you see, this one actually looks fun. Like I would love to try it out, right? It's looks like so anyway.
So I think that one takeaway here is just we want to test the hardware and also the algorithm. So we want to test the hardware and algorithm to try to solve more different tasks. Like so we proved that the current humanoid hardware and algorithm can solve these highly dynamic tasks. This might point a direction for the future work. Yeah, and the second one is like I think the hierarchical decomposition can sometimes simplify the problem. Like, because I tried the end-to-end and found it cannot work very well. Yeah. So, as I said before, I think there are lots of limitations and there is still a long way to go to achieve like champion level humanoid table tennis.
Yeah, this is really awesome. Yeah, thanks so much for the sharing, Zhi Su. Maybe just to, I guess, wrap things up, like this is a common question we always ask towards the end. Are there any like papers that you come across recently that really piqued your interest that you want to share a little bit? So our listeners can also go and read that paper. Zhi Su, thank you so much for making the time. All the best with your applications. Yeah. Definitely looking forward to your future work. I think you're gonna do. I hope you continue this line of work though. I think this is super cool. Yeah, I would love to see you continue to more of this with the humanoid in sports. I think that's it's the kind of thing that makes people who are not doing research, just get attracted to research, right? Yeah. Very
there are demos that like immediately make you think like, wow, robots can do cool stuff, and this is like it's actually kind of rare, right? And this one's one that really clicked. It works. It's nice. A lot of fun.
Yeah, 9 out of 10 of our podcast is about like picking an object and putting it here.
Right.
And that's wonderful paper. Whereas yours is, oh gosh, you can move rally with
it's
the
very dynamic. It's very cool. Yeah.
Yeah.
Oh,
So
interesting.
yeah, it's really captures people's attention. Okay, that's great. Thank you so much for your time again, Zhi Su. Yeah, looking forward to.
So I think, as with a lot of people, I think I saw this robot playing tennis demo video online. I thought I was super impressed by it. I think it's very cool. It's like a somewhat straightforward recipe, right? But he has a nice like division where you track the object and then learn a whole body controller to put the thing into place. It sounds like everything came together really nicely. I really like that this shows how dynamic the tasks that you can perform with one of these robots are, and it does involve like interacting with the world, which we like as he mentioned at the beginning, right? Which we generally don't see with a lot of these Unitree demos, where they're all like the robot like dancing or doing a cartwheel or whatever it is, where those aren't like all that. In the end, that doesn't matter that much, right? Like we really want the robot to be able to touch stuff and do things, and this is like a really cool dynamic example of that. So I really liked it. That was cool work. Really impressive that he pulled it off as an undergrad in 3 months. Nice stuff. So much more than I did back then. Yeah. All right. Yeah. So how about yourself? What do you think?
Oh, exactly like I said. Like I think the demo is impressive. Not just that it's impressive, but it's also like very. I thought it's a kind of demo that really can get like people outside of like our own little circle of doing like robotics interested in like just getting then people know, hey, the hardware is actually can do this, right? And then maybe draw more attention and more maybe like your next undergrad to do like pick robotics instead of like doing traditional AI stuff, right? Yeah, it seems to me. Yeah, I guess like but like he mentioned, there are a lot of limitations with his setup. Not everyone have a mocap, that is like, room scale, motion capture, at high frequency. That setup is not trivial. I mean, he rely on a lot of like physics, classical, technique to basically just shortcut the whole problem and make it solvable. And given that he is 3 months, I think is already impressive, very impressive.
Right.
So that's why I was asking, wait, dude. He did it in 3 months, man, in a short stay in a foreign country.
Right. I thought there were tons of places where it really feels like you could go a bit farther with more learning, like, and more, obviously a lot more time and resources and whatnot. Like just learning a better model, like of the better dynamics model for the ball. Like even if it wasn't part of the rest of the system, you could learn a better dynamics model for it. So because like one of the big problems that he was having was just the accuracy was really poor because the model of the ball was bad. Right. There's lots of little things like that I feel like, I mean, yeah. But I mean, it's impressive. I agree. Yeah, lots of the limitations, like the motion capture setup. That's something where I feel like it'll get better with time as time goes on. Because like I think we just need more compute and longer kind of time windows and stuff to be able to do that with vision and better cameras on our robots. And like it's exciting because it feels like makes all this stuff feel very real, right? In some ways. Yeah.
Yeah, I mean, what he's already proven is as a real world demo is what the G1 itself as a hardware. It can do. You can do basic rally, right? Yeah, not the crazy one, but I can do basic ones. So I think it's just a matter of maybe doing. Yeah, but I think that the whole mocap part, I think, I believe, the next 1 or 2 papers that's along this line of work will probably. What I'd love to see is taking out the mocap and just use the vision and maybe active vision when there's a G2, let's say that has actuated neck. Then I think you can do really what a human do, which is basically purely vision, right? From the vision, you gauge the position and then use that to gauge what you should do with the ball coming that way.
Mm-hmm.
So yeah, because I mean, it's not realistic for most environment for you to have a predefined mocap somewhere in a room, right?
Right.
What you really want is all the capabilities a humanoid can do is sitting with the sensors that the humanoid already have, right? So that could be your LiDAR, your cameras and all that. Yeah. So yeah, but still impressive.
Yeah, I mean, this is why I think it's one of those things where it's like there's a clear trajectory, right? Like if it has like a Thor or something in it, right? The computer, if the robot has some real beefy compute in it and can actually process like 3 or 4 frames, then it can estimate the position of and velocity. I'm sure, at least especially if the ball's brightly colored, right? So you're just talking about, you're not talking about something fundamentally different. You're talking about like massively increased, a reasonably large increase in the amount of compute and data that you need, but attractively increased one that I think, like, if you want to do, I'm sure someone could do this on board in a year or two, in a year. I don't think see anything fundamentally stopping you, right? Like, whereas there's a
Yeah.
makes sense. I don't know.
Yeah. Yeah, I'd love to see more people try
Hope so.
something like this. Yeah, it's a very fun thing to try. And you know, as you do this like sports thing, especially humanoid, like there's just new capabilities that's also unlocked by research. So yeah. Okay, sounds good.
I really
Cool.
like seeing
Yeah.
the long rallies. That was the other thing. I really like seeing the long
Yeah.
rallies. Anytime you get like one of these like longer, like, hard to predict interactions going on in a robot, it's like that's really cool. You don't see that a ton. But
Yeah.
sorry.
Yeah,
Anyway.
it's not like a 10-second episode. You know,
Right.
it's a continuous
It's
thing.
harder to cherry pick too. Like unless you're really sitting there all day, just
Yeah.
But
Exactly. Yeah. The longer the video, the better.
yeah, exactly.
In general.
Exactly. Right. Cool.
Yeah. All right, cool. We'll talk soon again, Chris.
Yep.
Okay.
Bye.
All right.